In this video, we are going to explore how to write a vector as a linear combination of other vectors in a vector space. This topic is from chapter 4.4, which is about spanning sets and linear independence. Our learning objectives for this video series for section 4.4 also include determining whether a spanning set S of vectors in a vector space is a spanning set of the whole vector space V. Determine whether a set of vectors in a vector space V is linearly independent, and proving results about spanning sets and linear independence. So this first video will cover linear combinations, and then we will have subsequent videos covering spanning sets and linearly independent definitions. So let's start with what it means to be a linear combination. A vector V in a vector space capital V, which we denote just as capital V, or you can use the fancy V with the lines as we did here. Either way is okay. If you just say capital V, we'll know you mean a vector space. So a vector is called a linear combination of the vectors U1 through UK, an arbitrarily long list, in the vector space V, if and only if this vector V can be written in the form of a linear combination of those vectors U1 through UK. When we say linear combination, we mean a constant multiplied by each of these vectors U1 through UK, different constants for each vector, of course. Constants are C1 through CK. You can think about it as a scalar multiple if you're thinking about it as scalars and thinking about the vector space might be matrices or different types of spaces or ordered pairs. So if V can be written as a sum of these constants or scalar multiples multiplied by each of the vectors U1 through UK, then V is called a linear combination of those vectors. So let's take a look at examples. So in this example, we're going to write this vector V equals -1, -2, 2. So this is in R3, a 3-tuple, as a linear combination of the vectors in the set 2, -1, 3 as the first vector, and 5, 0, 4 as the second vector, if it's possible. So the equation that we're solving here is V equals some scalar times U1. So I'm going to call our first vector here U sub 1. And some scalar times our second vector. So I'm going to call our second vector here U sub 2. And these scalars are going to be what we solve for. So I'm going to substitute in our vectors U1 and U2 along with vector V. So here's vector V. That's -1, -2, 2. And we're going to see, does that equal some scalar C1 multiplied by our U1 vector here, plus some scalar C2 multiplied by our U2 vector here. Okay, so I'm going to distribute the scalar through for U1 and U2. So we get 2C1, -1 times C1, and 3 times C1 for C1 times U1. And we get 5 times C2, 0 times C2, and 4 times C2 for the product C2 multiplied through by the vector U2. And then we can combine like terms. So we can combine all of the first tuples. So we take the first tuple that was 2C1, and we add to that the 5C2 from the first tuple of C2U2. And then the second entry, or the second tuple, if you're thinking about it as a 3-tuple, like X, Y, Z. So the Y position would be -1 times C1 plus 0 times C2, coming from these entries right here in the addition. And then our third entry, or the Z entry, or the third tuple, is 3C1 plus 4C2, coming from the 3C1 plus the 4C2 in the second part of the addition. Okay, so we know these need to equal the 3 values in our 3-tuple for V, so we can set up the equation 2C1 plus 5C2. So this whole equation right here equals -1, and so forth, setting each of these equal to the values in V, which are over here in this column. So then this becomes something we can solve with matrix multiplication. So we take our coefficients. So here's our coefficient matrix. And we multiply those by C1, C2, and we should get out the values from V. So we can solve this by finding reduced row echelon form, and we'll do plenty of examples in SIMPy with reduced row echelon form, so I'll leave this one for you to check. So if we put this matrix here into SIMPy and do reduced row echelon form, we would get this resulting matrix here. So that gives us this equation that, okay, 1 times C1 plus 0 times C2 equals 2. Let me write that out over here for us. And then from the second multiplication through, we get 0 C1, so taking this and multiplying it by C1, C2, and knowing it should all equal -1. So we get 0 C1 plus 1 C2 equals -1. And then our last multiplication, we get 0 C1 plus 0 C2 equals 0. So that's already taken care of for us. So solving this, we get C1 equals 2 and C2 equals -1. So we can write our vector V here as 2 times U1 minus 1 times U2, which is just written right here for us. So it is possible to write V as a linear combination of these vectors U1 and U2 that were given to us in the set S. All right, let's take on another example. So now we are going to write the vectors V equals -3, 15, 18, and W equals 1/3, 4/3, 1/2 as linear combinations of vectors in this set 2, 0, 7. So I'm going to call this U1. 2, 4, 5, I'll call this U2. And 2, -12, 13, U3, if possible. Okay, so let's start with V. So for V, we need to solve V equals C1 U1 plus C2 U2 plus C3 U3 for these scalars C1, C2, C3. Okay, so I'm gonna plug in our vectors here. I'll switch colors. So our equation is going to be -3, 15, 18, that's vector V, equals C1 times 2, 0, 7. That is the vector we're calling U1, plus C2 times 2, 4, 5. That's the vector we're calling U2, plus C3 times 2, -12, and 13. That's the vector we're calling U3. And then if we do the same thing for W, so W is also going to be some other set of constants. I'm going to say W equals D1 U1 plus D2 U2 plus D3 U3, where D1, D2, and D3 are scalars. Then we're going to get a second equation for W that is going to be 1/3, 4/3, 1/2, and that's going to equal D1 times vector U1, so that's the 2, 0, 7, plus D2 times vector U2, so that's 2, 4, 5, plus D3 times vector U3, so that's 2, -12, and 13. All right. So I'm going to translate these to systems in matrices. So I'm going to go ahead and translate these to a system for V. So that's going to be 2, 2, 2. And that 2, 2, 2 comes up because if we head back to the vector arrangements here, we see, okay, the first elements of U1, U2, and U3 are all 2. So we're going to have 2 in the first row there. And then following the next elements, we're going to have 0, 4, negative 12. And then following the third elements of those vectors, we're going to have 7, 5, and 13. And then we're going to multiply this by our C1, C2, C3. Those are the scalars we're trying to find. And that should equal vector V for us. So vector V is the negative 3, 15, and 18. And then we're going to do something similar for vector W. So for vector W, we're going to have the same coefficient matrix, 2, 2, 2, 0, 4, negative 12, 7, 5, and 13. And then we're going to multiply these by D1, D2, D3. So we're working in tandem here to solve for U and V. You could also, or sorry, V and W. You could also go through and solve for V and then solve for W. You don't have to work in tandem as we are. And so for vector W, our values that this should equal are 1/3, 4/3, and 1/2. Okay, so I am going to start with the matrix for V and head over to Simpy and do that in reduced row echelon form, and then we'll come back and do the same for W. So the matrix for V is going to be augmented with the solution 2, 2, 2, negative 3, 0, 4, negative 12, 15. And in the bottom row, 7, 5, 13, and 18. So I'm going to go head over to Simpy and put this into reduced row echelon form. And then we'll come back and use that to solve, if possible, for the linear combination. Okay, so here in Simpy, I'm going to call my matrix V. We'll see if Simpy likes V. Sometimes it's picky about the letters I use because they already stand for something else in the system. So V is going to be my matrix 2, 2, 2, negative 3. In the top row, 0, 4, negative 12 in the second row. Oh, and I also need my solution value, 15. And then in the third row, 7, 5, 13, and 18. And then we'll type V and just double check. How does it look here? Looks good. And then we'll say RREF of V. Oh, it's V.RREF with the parentheses. And then we just want the first result. So I put 0 in brackets there. Here we go. So here's our reduced row echelon form. And this is going to allow us to solve. So I'm going to head back to the whiteboard. Okay, so in reduced row echelon form, I now have 1, 0, 4, 0 in the first row. In the second row, and you can put the little dashed line through here if you want, so that you think about that fourth column as the solutions. Then in the second row, I have 0, 1, negative 3, 0. And then in the last row, I've got 3 zeros and a 1 in the solution space. Okay. So what this tells us is, but for that last row, 0 times C1 plus 0 times C2 plus 0 times C3 equals 1 has no solution. We see that right away. So since there's no solution, V is not a linear combination of the vectors in S. And for this S, I just kind of write a big S with some hooks at the end. You can write just capital S and we'll know. You can try to add, you know, some lines here to make it look like the S that we saw in the font. Okay, so now we're gonna pursue W. So now for W, our matrix augmented with the solution is going to be 2, so we'll put a W up here, 2, 2, 2, and our solution for W is 1/3, 0, 4, -12, and our solution here is 4/3. And then the bottom row, we're going to have 7, 5, 13, and 1/2. So I'm going to head over to Simpy and do reduced row echelon form for this. Okay, and I'm going to be a little lazy, so I'm going to arrow back up to get where I entered matrix V, and I'm just going to edit that because I know I just have to change the 4th column here. So those 4th column values I'm going to change to be 1/3, 4/3, and 1/2. And we'll see if Simpy likes that. So if I type W, here's my values here, and then I want the reduced row echelon form for W, so I do W REF in parentheses to run the reduced row echelon function. And then I just want the first result. I don't care about any row swaps, so I put 0 here in brackets. And here's my reduced row echelon form of the matrix. So let's take a look at it. So I get here 1, 0, 4, and -1, 6 in the first row. And then I have 0, 1, -3, and 1/3 in the second row. And in the third row, I've got all zeros. Okay, so the zeros all in the third row tell me that this has an infinite number of solutions. So we can think about D3 as a free variable. So we can say D3, or we can call it T, is a free parameter. Since it's a scalar, we'll call it a free parameter. So I'm going to arbitrarily let D3 equals 0 here to solve this system. And then D1, if I work through my equations here, D1 is going to be -1/6 based on the first equation, because the first equation is 1 D1. So then D1 equals -1/6. And then the second equation, if D3 is 0, then we're going to get D2 equals 1/3 based on this right here, because -3 times 0 gives us D2 equals 1/3 there. So we can write W as -1/6 times this vector 2, 0, 7. Remember, this was U1, plus 1/3 times the vector 2, 4, 5. That was U2, plus 0 times 2, -12, and 13. That was U3. So W can be written as a linear combination of the vectors in that set S. So we can say here, this is one solution for W. Now we know, since D3 is free, that there's infinitely many solutions. So you just change D3 to some other value, and then that's going to change what you get for D1 and D2, and then you've got yet another solution for W. Okay, so remember also that vectors or vector spaces we can think of as matrices. So we know the set of m by n matrices form a vector space of the real numbers. Also the set of square matrices, that's just a subgroup of the rectangular matrices. So we are going to look here at a vector that's a 2 by 2 matrix. So now in this example, vector v is the 2 by 2 matrix with 24, negative 48 in the first row and 57 and 20 in the second row. And then we are going to write this as a linear combination of this set of vectors that I'm going to go ahead and call these matrices U1, U2, U3, and U4 if possible. So this is a good reminder in this example that matrices can be vectors as well. So when we say vectors, we're used to thinking about the lists of numbers, but also a matrix can be a vector, not just a pair of numbers or a tuple, a 3-tuple or 4-tuple, etc. Okay, so what we need to solve is this equation, v equals c1u1 plus c2u2 plus c3u3 plus c4u4 for scalars C1, C2, C3, and C4. All right, so I'm going to plug in our vectors and write this out here. So we have got our vector v is 24, negative 48, 57, and 20. And that's going to equal C1 times 1, 2, negative 5, 4, plus C2 times U2, which is 2, negative 7, 6, and 2, plus C3, which is 4, negative 9, 11, and 12, plus C4, which is, oh, that's a 4, which is 6, negative 5, 4, and negative 5. Okay, so this is going to give us a massive system. So we'll distribute the C's through first. So we're going to get 24, negative 48, 57, and 20 equals 1C1, 2C1, negative 5C1, and 4C1. And remember, when you multiply this scalar by the matrix, it goes to every single element in the matrix. That's why we're able to write our matrix this way on our way to creating this massive system. Then in the second matrix, we get 2C2, negative 7C2, 6C2, and 2C2. And we're going to have plus 4C3, negative 9C3, 11C3, and 12C3, plus over here we get 6C4, negative 5C4, 4C4, and negative 5C4. Okay, those are 4s. So we're going to head over to get a system and a resulting matrix. So our system is going to be 1C1 plus 2C2 plus 4C3 plus 6C4 equals 24. So these are the values from all of the first entries in these 2 by 2 matrices. And then I'm going to go to the second entries to write my next equation. So my next equation in this system is going to be 2C1 minus 7C2 minus 9C3 minus 5C4 equals negative 48. And I'm able to write this system because I know from matrix addition and properties that all of these entries are going to need to add up to make the resulting entries in matrix V. Okay, so then the next entries in row 2, column 1 are going to give us this system: negative 5C1 plus 6C2 plus 11C3 plus 4C4 equals 57. And then our last entries are going to give us 4C1 plus 2C2 plus 12C3 minus 5C4 equals 20. And you can see those are just the values that were in row 2, column 2, added up to equal 20, which is in row 2, column 2 of vector V. Okay, so now I want to translate this into a matrix that I'll be able to solve. So I can rewrite this as a coefficient matrix. 1, 2, 4, 6. 2, negative 7, negative 9, negative 5. Negative 5, 6, 11, and 4. And 4, 2, 12, and negative 5, multiplied by our scalars, which are C1 through C4. And this should all equal our solutions, 24, negative 48, 57, and 20 from right over here, as well as being the values in matrix V. 48. Okay, so let's set this up as an augmented matrix and then go ahead and run reduce for echelon form on it. So our augmented matrix here is going to be 1, 2, 4, 6, 24 in the first row. 2, negative 7, negative 9, negative 5, and negative 48. Sorry, I'm not lining these up as best as I would if I were able to type these out or write on a chalkboard. And then in the third row, we've got negative 5, 6, 11, 4, and 57. And then in our last row, we've got 4, 2, 12, negative 5, and 20. So let's head over to Simpy and do some reduced row echelon form to solve this system. All right, I'm going to call this matrix A, just arbitrarily. So our first row is 1, 2, 4, 6, and 24. Our second row is 2, negative 7, negative 9, negative 5, and negative 48. Our third row is negative 5, 6, 11, 4, and 57. And our last row is 4, 2, 12, negative 5, and 20. All right, so here's our augmented matrix. And so let's do reduced row echelon form on matrix A. And here we go. So this looks actually really nice. Like we're going to get straight solutions because we've got identity matrix augmented with solutions here. So let's write this out here. So we have 1, 0, 0, 0, negative 2. We have 0, 1, 0, 0, 1. So this tells us right away, okay, C1 is -2, C2 is 1, then we have 0, 0, 1, 0, 3. So now we know C3 is 3. And we've got 0, 0, 0, 1, 2. So C4 is 2. Okay, so then we can write this out as 24, -48, 57, and 20. Our original vector V, or matrix V if you want to call it that, is going to be -2 times 1, 2, -5, 4, where this was U1, plus 1, because C2 is 1, times our U2, which was 2, -7, 6, and 2, plus 3 times U3, which was 4, -9, 11, and 12. And then we've got plus 2 times U4, which was 6, -5, 4, and -5. So in this example, there is one unique solution for writing V as a linear combination of the vectors in S. So we have seen in this video all three examples. Here's a situation where we have one unique solution. We got unique solutions here for C1 through C4. We saw in our previous example an infinite number of solutions because we had a free parameter here. Our third scalar D3 was a free parameter. And we saw in the example with V, solution where we had no solution because we got an equation that didn't make sense after our reducer echelon form. You couldn't have 0 C1 plus 0 C2 plus 0 C3 equals 1. So we were able to conclude V was not a linear combination of vectors in S. So these are the three possible types of solutions you might get for solving linear combinations of vectors. You get no solution, you could get infinite number of solutions, or you could get one unique solution as we did here. So in the next video, we will take a look at spanning sets and see that relationship between spanning sets and linear combinations.